Hi guys. So today is actually our last day of new content. So after today, we are going to kind of review a little bit, and really that's it for the year. This is really going to kind of wrap it up. And this, honestly, guys, isn't too new for you guys. It's very similar to what we did at the beginning of the exponential part of this unit. We're just going to look at how to solve these algebraically and look at a few other equations to kind of add into the ones you guys have already seen so far. So starting off, just looking at all these different formulas, all of the ones in the top row are the ones that you already looked at so far earlier in this online instruction time. So this first formula was the one that you used for interest that was compounded a certain number of times a year. So if it was compounded monthly, then n was 12. If it was compounded daily, n was 365. There's a specific type of interest that we said if it was continuously compounding. So continuously compounding interest is when we use this PERT formula. So that's our continuously compounded interest. Then the one that we used for a lot of our growth and decay was this real simple 1 plus or minus r, and that just depended, again, if it was growth or decay. Now, the ones that we're going to introduce today are a little bit more specific. So the first one you may have seen in chemistry. This is for half-life. So half-life is the amount of time it takes for a certain element to decay. So on this formula, A sub t, that's your amount after however much time. A sub naught right there, that's your initial amount. T is the amount of time that we're talking about in the problem. So your typical t value. So like let's say you want to know after 20 years, then t is 20. The H at the bottom, that's your half-life. So the actual half-life, how long it takes for that substance to decay and lose half of it. So that's the value that will go there. Double growth is almost the exact same formula, except instead of half, it's doubling. So again, if you're given information like this population doubles every 3 days, then the 3 would be that H. And then let's say you want to find how much there is after 40 days, then that's your T. So very similar formula. Then the next one is actually the exact same formula as the continuously compounded interest formula. There's no difference in those two formulas. The way that second one works, you're going to see some situations where our normal growth and decay equation don't really make the best sense. Typically, these problems will talk about something called a relative growth rate, or it may just say, talking about how it's compounding continuously, etc. This is most likely used most often when we're talking about population growth, or you're talking about growth of bacteria in a culture, something along those lines where it's not this nice, pretty, okay, here's my 1 year total, now it loses 10%. Now here's my next year, now it loses 10%. Where again, you're growing on the growth. So as people and populations, as they grow, it matters, as it's happening, you're basically getting, I don't want to say interest on the interest, but that same kind of idea. For today, it should tell you pretty clearly when to use this equation. If not, again, look for the term relative growth rate, and that's the one that really kind of describes this new equation. But again, it's not a new equation. It's literally the same as the PERT equation. It's not necessarily principal, and we can use them in other situations. All right, so the only thing that's going to be different today than what we did earlier this year is going to be that we're, instead of just using the calculator straight up, now that we know how to solve exponential equations using logs, we are going to solve these equations algebraically. So starting with the first one, the half-life of a radioactive element is 40 days. If you start with 200 grams, after how many days would you be left with 75 grams? So we're going to start using the half-life formula. So again, I want to know when I'll be left with 75. I'm starting with 200. I don't know how long it will take, so that's my X. I do know the half-life, and that's 40 days. Now, whatever period you use for both of those values, it needs to be consistent. So since this is 40 days, your answer is going to be in terms of days. So now, again, we could just do the y1, y2 and find the intersection, or we could do y equals, and then we could do our x cal for 75. But again, we want to show the algebra here to kind of review the solving stuff that we've already done. So in order to solve this algebraically, what I'm going to do is start by dividing by 200. And then at this point, I can rewrite this as a log. So this would be log base 1/2 of 75 over 200 equals x over 40. Then your last step to get x by itself, you would just go ahead and multiply by 40. So I get 40 log base 1/2 of 75 over 200 equals x. At that point, you can go ahead and plug it into a calculator, and I need to pull mine up. And that's going to give me a value of 56.6. And remember, since the half-life was in terms of days, this is in terms of days as well. All right, so let's go ahead and look at another one. So this next one, we're looking at the number of bacteria in a culture is doubling every 3 hours. So we're going to use very similar equation to that half-life one, but again, it's doubling this time. So it would be A sub T is A naught 2 to the T over H. All right, so it says there are initially 200. It's doubling. And we want to know how many there are after 2 days. And it's doubling every 3 hours. So remember, these two things need to be in terms of the same unit. So if it's doubling every 3 hours, I know how many bacteria there are after 48 hours. So your T would be the 2 days, which we're using in terms of hours. So this would be 48 divided by 3. Now this is one you don't really need to show a lot of work for because we can just plug this straight in as is. There's not really much more you can do at this point. But go ahead, plug it in, and we'll end up with 13,107,200. All right. Next one, the population growth. Again, this is one where we're going to talk about the relative growth rate, so we're going to use that E equation. So this one's a little bit different. It doesn't tell us what the rate is. It tells us the rate, it tells us the population at a certain time. It tells us the population at another time. So what we need to do is we need to solve for that rate. Once we know that rate, we can go back and use it to answer the second part of the question. So right now, we're just going to use the information we have. We're going to treat 1990 as our initial amount. So in 1995, it raises to 45,000. So that means that 45,000 is equal to 42,000 E to the R. I don't know what R is, that's what I'm solving for. And T is the time it takes to go from 42,000 to 45,000. Well, that took 5 years. So now we can go ahead and divide by 42,000, and I'm just going to reduce this a little bit. We can rewrite this as a log. So this would be the natural log of 45 over 42 equals 5R. Divide by 5. And I end up with a rate of 0.0138. Now, one thing I will tell you, if you're doing this on a calculator, leave that value in your calculator. Instead of using that rounded decimal, on the next step when we use that rate, I want you guys to use that previous answer. So you can scroll up and press enter, or you can use that ANS button. That way you're getting the exact rate and not the rounded rate. If you use the rounded rate, it's okay, but you're going to get a little bit of a different answer than what you're seeing on mine. And that's okay, but just keep that in mind. The most exact answer and our best answer is going to happen when we don't round this value, and instead we use that exact answer from the calculator. All right, so now let's go ahead and answer that second question. So we found the rate, that's the 0.0138, that's 1.38%. Again, we're going to use the exact answer though for our next calculation. Next part is find the population in 2002. All right, so our initial amount is still 42,000. E, we now know that rate, and again, we're going to use that previous answer so it's exact. And then the time it takes, so from 1990 to 2002, that's going to be 12 years. This one doesn't require a lot of algebra. Plug it straight into your calculator, and again, use that previous answer to get that exact value, and you're going to end up with 49,563. All right, so the next question on there is, again, straight exactly what we did back in exponential. You deposit money into account. It gives you the interest rate. It's compounded continuously. We want to know how long it'll take for the account to have $5,500. The only difference this time is we are going to actually solve algebraically now that we understand those steps. So to set this up, I would do 5,500 equals 5,000 E to the 0.0125 t. T is what I'm solving for. All right, so at this point, I'll divide by 5,000. That gives me 55 over 50. Rewrite it as a natural log. So the natural log of 55 over 50 is equal to 0.0125 t. Divide by 0.0125 on both sides. Plug that in your calculator, and you're going to end up with your value of about 7.6 years. Again, this is a question you guys have done before. The only difference here is you now understand this algebra to actually get to your answer, as opposed to just doing your intersection or your xcal. All right, so the last few are actually going to be very easy on the algebra, but this is just showing you guys a few examples of some real-world things that are log-based. So in chemistry, you probably have already seen this next one, talking about pH. So pH is based on that hydrogen ion concentration. Depending on your pH value, tells you if a solution is acidic or basic. So that equation, it's negative log of those that hydrogen ion concentration. So example here is apple juice. Okay, let's say it has a hydrogen ion concentration of 0.0003. So to find that pH value, it's pretty simple. I'm just going to plug it in. And again, this really is just showing you guys just some examples of some things that really are log-based in the real world. Plug that straight into a calculator, and it tells you your value, which is 3.523, which means that this solution is acidic. All right, looking at our next one. So decibels, that's another thing. Determining decibels is also log-based. Anything that's above 85 can cause some hearing loss. It says that the decibel is equated, it's 10 times the log I over I naught. Okay, that I naught at the bottom is threshold sound. So it's really kind of that ratio there. So this first question, it says a cat's purr is 316 times as intense as threshold sound. So we don't know what that threshold sound is, but let's say if it's 1, then the I for the cat's purr would be 316. If this is 2, this would be 2 times 316. So whatever we use for that value, it doesn't matter because that ratio is going to be 316. So this would just be 10 log 316. And again, this is another one. It's just plug in and go, and you end up with 25 decibels. Which makes sense because 85 decibels is going to cause hearing loss. Okay, this is a whole lot less than that. And a cat's purr is not very loud. All right, then the last one. This one I thought was actually just kind of interesting. So this is an article actually that my mom found and sent to me. But it says that usually when we talk about dog years, we just multiply by 7. But experts actually found a more accurate way to equate dog age to human age is with this log equation. So D is the dog's age, H is the human equivalent. So based on this method, we want to determine the human age of a 15-year-old dog. So again, the human age would be 16 times the natural log of 15 plus 31. Plug it in, again, just straight up plug it in, and we end up with 74.329 years. So a 15-year-old dog is about a 74-year-old dog. All right, so that's really it for today. Again, pretty similar to what you've already done, just getting some extra practice in on solving these algebraically as opposed to just using the calculator. You've got your practice problems. You'll submit for a completion grade. If you need help, you can email me, do that video request, or join that Thursday Zoom session. One thing that's a little different this week, you'll notice there is no weekly assessment. Really, that's going to be kind of covered in your Thursday options. So when you get to Thursday, there's another video that explains it, but you have 2 options for Thursday. One of them is kind of that weekly check like you guys are used to seeing, but it is going to combine some things from some previous weeks in there, so it's going to be a little bit more cumulative. Your other option is there's a little project that you can do. It's a little bit more creative and a little bit less of the straight up math. It's really just a matter of which one you guys prefer to do. So go ahead if you want to jump into the Thursday folder just to get a preview and just kind of maybe watch the video to see about what your options are. But again, just a little bit different on the weekly check for this week.